Good morning. Today we are going to talk about a new topic called review of graphs. Graph is the fundamental method we are going to use throughout this class to analyze program. Graphs is a branch of mathematics, and you may be considered topology. Okay, that's the sub area it belongs to, and you have learned graphs already in data structure, for example. I think that's all we need to understand or to use in this class. Okay, and in this class, we are going to use directed graph. Because when you talk about graph, there's undirected graph. What is undirected graph? It is like this. Undirected graph is that I have two nodes, for example, A and B, and they are connected. Okay, in an undirected graph, that means you can come to me, I can go to you. That's called undirected. And but here we are interested in a directed graph. That is like this. That is only C can go to D. Okay, and the D cannot go to C. So this is the directed graph that we are interested in here. So you say, okay, why are we only interested in directed graph? Because we want to model our program execution. Apparently, in our program execution, there's a sequence, right? We follow the program counter, okay? Because there's a sequence. You go from this statement, go to next statement. So you cannot reverse unless your program specifically specifies that. So otherwise, we have to go in one direction, and that's why we are going to use the directed graph. So here we are going to use the directed graph. So here are some fundamental points about directed graph. For example, here I have a graph, right? And how do we represent a graph like this? So a graph consists of vertices and edges. The vertices in this particular case, they are simply node 1 all the way to node m, right? And then the edges, they are from h1, h2, So, and every single edge, there's a pair of nodes or a pair of vertices. So ni is the initial or the starting node, and the nj is the ending node. So, an edge basically is an ordered pair of nodes. So in this particular case, you can see that how many vertices do we have? We have vertices from n1 all the way to n7. Okay, so n1 all the way to n7. And how many edges do we have? We have h1 up to h6. So we have h1 up to h6, right? So here how do you represent individual edges? So here we have n1, n2. So that's the starting node, that's the ending node for h1. Okay, don't you think this is a piece of cake? We learned this in kindergarten. Okay, so and there are more terminologies. So we have the in degree. In degree means that how many ways you may get to a particular node. For example, n degree for n1. How many ways you can get here? There's no way. So it's 0, right? How many ways you can go to n2? There's only one way. So n degree is 1. Okay. For n degree 4, for node 4, how many ways you can get there? You can go in here, you can go in there. So in degree is 2. Out degree, that is how many ways you can get out of a node. So out degree for n1, how many ways you can get out of there? There are 2 ways, so on and so forth. Okay. So and the source node is this is the starting node, like n1. So it's in degree is 0. Sync node is there's no way for you to leave that node. For example, n5, that's a sync node. A transfer node is something in between. Directed paths, we say, okay, we talk about paths, right? We talk about directed paths, but here we are talking about slightly different kind of concept, okay? A directed path is like this. A directed path So we have, say, C1, C2, to Cn. So we call that this is a directed path. That is a directed path, okay? You can see that we go from C1, C2, we go directly to Cn. So we call this is directed path. Well, it's only one path, right? And how about semi-path? So a directed semi-path is like this. So I have a node here. So for example, I go to say this node 1, okay? So here we say, well, there is semi-path between node 1 and 2. You say, okay, we say that there's a path between 1 and 2. Yes, because you know they start from the same node. If they start from on the same node, then we call that there's a semi-path. And also, we may say that something like this. We say that say this node A, node B. We say that we also have some kind of semi-path between A and B. Okay, why is are there really there's a path between A and B? Yes, in the graphs concept is because they may reach the same node. Do you see that? So they may reach the same node. So in that case, we say that there's a semi-path between A and B. On the other hand, here, A1 and 2, they come from the same node, okay? You say, why do we care about this? Well, the reason we care about this is because, you know, here, there may be some inferences between 1 and 2, although it's not direct inference, right? You know, here, that's a direct inference, as you can see. But here, there may be some side effect. Haven't we talked about the side effect, you know, between 1 and 2? There may be some side effect. If you modify this, there may be side effect here. And then the same thing here, A and B, there may be side effect. So that's called semi-path, okay? So, with that said, let's go back to the PowerPoint slide. So that's what we say, it's called directed semi-path, okay? That is the two examples I show you. So by using a real graph, it is like this. There's a directed path. Well, I call it a path. We call it path. That means directed path. Directed path from N1 to N6. So from N1 to N6, right? Because you can see that from N1 you can go directly to N6. A semi-path between 1 and 3. So 1 and 3, you say 1 and 3, there's a because they reach the same node. Have you noticed that? So there's a semi-path from N, there's a semi-path between N1 and N3 because they reach the same node. They may influence the same node, okay? And also we have a semi-path between N2 and N4. N2 and N4. Well, because they came from the same node, right? So we say there's a semi-path. And N5 and N6 as well. Where's N5? N5 is here, N6 here too. So here you can see that they start from the same node. In this case, it's N1. So these are just terminology. So we also say that a graph is 0 connected, 1 connected, 2 connected, 3 connected. 0 connected is that you know there's no path between two nodes. There's no path. Just there's no connection in any sense. So between two nodes, I call it 0 connected. So for example, N1 and N7, where's N1? N1 is right here, and N7. Have you noticed that N1 is a loner? So in that case, N7 is not connected to anybody, so it's 0 connected. 1 connected is there's a semi-path between those two nodes, okay? So you say N2 and N6. Where's N2? N2 is right here. N6. Well, N2 and N6, they are 1 connected, right? Or they are a semi-path. Semi-path is that because they all started from the same node N1. So it's 1 connected. okay? Two connected, there's a directed path. There's a direct path, that is. N2, N1 and N6, N1 and N6, well, they are two connected because there's a directed path. From N1, you can go to N6 directly, two connected. Three connected is that I can go to you, you can come to me, okay? So it's a mutual connection. So here, N2 and N6, so N3 is right here, N6 is right here. So you see that there's a loop here. When there's a loop, you know, those nodes, they are three connected because I can go to you, you can come to me, okay? So in that case, it's called three connected. And a graph is connected. A graph is connected if all the node pairs, they are at least one or two connected. Okay, so in this case, because we have this loner, right? We have this loner and 7. This guy is not connected to anybody. So, you know, in this case, you know, nobody is able to get hold of N7. So the graph is not connected at all. Okay, and strongly connected is you know, is a subcomponent. You know, that's everybody is strongly connected. Okay, that is. So for example, in this loop, okay, strongly connected is basically we are talking about loop. So here you can see that those three elements, 3, 4, 6, okay? So in this case, you know, it's strongly connected only for a subcomponent, okay? So anyway, strongly connected is that everybody is three connected. All right, suppose I have a graph like this, okay? Well, here you can see that all the nodes, they are what? They are somehow connected, right? So every pair is you may say two connected, okay? Because there's a directed path. Well, not all of them, okay? They are at least one connected, okay? So they are at least one connected between any pair. For example, N2 and N4. N2 and N4, they are one connected because there's a semi-path here, right? So, but it's not strongly connected. What do you mean it's not strongly connected? Strongly connected means I can go to you, you can come to me. That's called strongly connected. So in this case, for example, from N2, sorry, you cannot go to N4, okay? You cannot go to N3 either. So because they cannot go to each other. So that's not strongly connected. On the other hand, the guy on the right. So here, if you notice, I added another node here called E9. By adding this one, the whole thing becomes strongly connected. Because now you'll be able to go to anywhere from any node, okay? For example, here is, oh, I want to go to N2. From here, can you go to N2? Yes, you can come here, right? And then N2. From N2, can I go to N4? Yes, you can. From N2, you can come here. And then you can go to N4, right? So strongly connected simply means that you could go anywhere from anywhere, okay? So a strong component of a graph is the maximum set of three connected nodes, okay? So in this case, you can see that 3, 4, 6, that is a loop, right? So, you know, those three nodes actually form a strong component. So these three strong components, they form a loop. So here you can see that 3, 4, 6, they form a strong component. And then, you know, semantically, you may say, okay, you know, N7 is strong component. Why? Because if you get to 1, you get to everybody, right? Yeah, well, if you want to say that. So you may say N7 is strong component because you go to 1, you go to all of the nodes, okay? So semantically, you may say that, okay? All right. Now we have not mentioned stars, right? Okay. Here is a number. Okay. Here is a number that I tell you, you are going to be very tired of. You are going to be very tired of. Okay, by the end of the semester. That number is called psychrometric number. cyclomatic number. How many stars are you willing to pour on this number called cyclomatic number? What? You only 1 million? Okay, 1 million is not going to be enough. Okay, you probably need more than 1 million. Okay, pour your stars on this cyclomatic number. Okay, just bear with me. Okay, so don't worry about what it means because later on we are going to use a lot of it. Okay, throughout the semester. Okay, cyclomatic number for a strongly connected graph. Okay, you needed to understand the precondition. The graph must be strongly connected. Okay, only strongly connected graph could use this formula. Okay, for a graph. Okay, the cyclomatic number is going to be the number of edges minus the number of nodes plus p. That is the number of strong components. I think in most situations, the strong component is going to be 1 because the graph is going to be strongly connected. P is going to be 1. Okay, in most cases, P is going to be 1. So it's the number of edges minus number of nodes plus 1. Okay. So in this case, that defines the cyclomatic number. Cyclomatic number can also be defined by the bounded areas defined by the graph. Okay, let's use the formula first. So here we know that it's strongly connected because you are able to go to any node from anywhere. So in this case, okay, let's count how many edges do we have. Okay, are you ready to count the number of edges? The number of edges is 1, 2, 3, 9, right? Wonderful. We have 9 edges, right? So from 1, 2, 3, 9. Okay, so we have 9 edges. So the number of edges is 9. Okay, how many nodes do we have? 1, 2, 3, 4, 5, 6, 7. So we have 7 nodes, right? So 9 minus 7 plus 1. So that is 3, right? So cyclomatic number for this graph is 3. Okay. Now you have to remember, always remember, if you want to use this formula, the graph has to be strongly connected. Okay. The second way of counting the cyclomatic number is to count the number of bounded area. So bounded area. Okay, are you ready? So this is bounded area, right? Do you see that? Okay, this little triangle is bounded area. And this one is another bounded area, right? Do you see that? And this is another bounded area. So totally how many bounded areas do we have? It is 1, you ready? 1, 2, 3. Amazingly, okay, it's also 3. So cyclomatic number is 3, right? By using the second method. There's a third method, okay? The third method is a lot of easy, okay? Hey, ladies and gentlemen, can I ask you a question, okay? Among the nodes here, among the nodes in the graph, which one is a conditional node? Which one are the conditional nodes, okay? So what do you mean conditional nodes? A conditional node is that it will yield true or false, right? So a conditional node is a node that will yield true or false, okay? So are you ready to count? All right, let's consider N1. Is this guy a conditional node? Is it? Yes, I think it is because do you see that there are 2 branches, right? So there are 2, the out degree is 2. So one of these branch must be true, and the other one will be false, right? Okay. Is N2 a conditional node? No, this is not a conditional node because there's only one outcome, right? How about N5? Is this guy a conditional node? No, because there's only one outcome. N7, no. N6, is this a conditional node? No, because there's only one outcome. N4, no, because there's only one outcome. N3, is this a conditional node? Yes, because you can see that there are 2 outcomes, right? So one of them will be true, one of them will be false. Okay, so you'll be able to memorize this graph. Okay, so here you can see that how many conditional nodes do we have. So this guy is a conditional node. This guy is a conditional node, right? How many conditional nodes do we have? We have 2. Okay, so with that said, I'm going to show you the third method to count the cyclomatic number. Okay, the third way to count the cyclomatic number is quite straightforward. Okay, so we say that this one represents the cyclomatic number. The third method is simply number of conditions plus 1. Okay, so this is the third method to calculate the cyclomatic number. So ladies and gentlemen, how many conditions do we have in this case? Well, you know, as we mentioned that there are two conditions, right? That is node number 1 and the node number 3. Okay, so we have 2 conditional nodes. So how many do we have? So it is 2 plus 1. So again, it also yields the same number of conditions. Isn't that amazing? Yes, so we also reach the same number 3. Okay, so there are 3 ways to calculate the cyclomatic number. You can do the formula counting. If you have time, you can count all the edges and then nodes and then, you know, plus 1. Okay, or you can count the bounded area, or simply just count the number of conditions. In this case, 1, 2. There are 2 conditions. Okay. Program graph. You know, the reason we study graphs is that we want to use it in our program. We want to represent our program in terms of graph. Okay. All right. So here is the notation we are going to use. So the first one is sequence, right? So we have sequential statements, M1, M2, M3, right? So in terms of graph, there will be simply, you know, a series of nodes, right? M1, M2, M3. Of course, they are directed. There's a sequence, so they will be executed sequentially. Okay, so that's a sequence, right? And if-then statement. So here, do you see that there's a condition here? When the condition C is true, when the condition C is true, where would you go? You are going to M1, right? So here you can see that, ladies and gentlemen, do you mind put a mark T when it is true? So put a mark T here on this branch, okay? So when it is true, you will go to M1, okay? When condition C is false, when it is false, where would you go? You will go directly to M2, right? So you just bypass, okay? So here, this is if-then. How about if we have else like this, right? So this is what we learned in kindergarten, right? So here, if the condition C is true, so please put down a true here, okay, T here, and this one is false here, F here, and the same thing for the if-then here. So we should put down an F here, okay? So this is the F branch. So when it is condition C is true, we go to M1. When condition C is false, we go to M2. Okay, so that is that's the program graph for this if-then else, right? Okay, and then if we have the switch statement, okay, you know, you all know switch statement well. Depends on what the value of a variable is, right? You know, sometimes we call it case statement. Depends on what language you use. So you may, so you have multi-way decision, depends on what it is. So you may go to different statements. Ladies and gentlemen, I want you to know that this graph, this particular graph like this is not acceptable, okay? This program graph here is not acceptable in our class. Although traditionally this may be fine for other purposes, but for this class, this one would not be accepted. You say, why this one? This one looks awfully easy to understand, yes, but for our purpose, because we want to calculate cyclomatic number. Okay, we cannot use this graph. You say, oh, okay, well, if we don't use this one, which one are we going to use? We are going to revise it into this format, okay? So this is what we had, right? But in this class, we want to revise it into or refine it into conditions. Ladies and gentlemen, do you remember how many outcomes a condition would yield? A condition will yield 2 outcomes, right? You know, for example, C1, it will yield true and false, right? For in this case, for example, the value is C1, I will go to M1, okay? If it is false, I go, it's not C1, I go to next one. See if it is true. If it is true, I go to M2, okay? So do you see that? So I'm going to use quite a few conditions, okay? Instead of just checking the value, okay? So in this class, this is the way we are going to use, and we are not going to use that. Is that fair? Okay, I'm going to show you examples, what I meant by that, okay? So just keep in mind, this is the kind of graph we are going to use. We are going to have conditions, and every single condition would provide only true or false, like this, true or false, okay? All right. So this is not what we are going to use. So we are going to use what I just mentioned in the note. Okay. So how about a loop? So here you can see that we have a pre-test loop. So if the condition C is true, we go to the loop. Okay. So the condition C, if it is true, so mark this branch true. If it's true, we go in there. If it is a false, we go out. Okay. And a post-test loop. Post-test loop is like the, you know, if the condition C is true, when it is true, we loop, we iterate again. So we go to the loop. When it is a false, we go out, right? So, and this is what we learned in kindergarten, in programming kindergarten, okay? So it's quite straightforward. So are you ready? Are you ready for an example? So for here, okay? So here you say, okay, this is awfully simple program, right? So here you can see that statement 1 is here, and then we go to condition. If it is true, we go to S2. If it is false, we go to S3, and then we come back to S4 right here. And this is a pre-test loop. So if when it is true, we go into S5, and when it is false, we go to S6. So this is the program graph, right? It's quite straightforward, isn't it? Okay. Now, but that's not really what we want. Okay. What we want is that, well, that's what we want, a program graph, fine. But my question is that, ladies and gentlemen, what is the cyclomatic number for this guy? What is the cyclomatic number for this guy? Are you ready for this? Okay, cyclomatic number for this guy, you can see that, of course, you say, oh, this is not strongly connected. The graph is not strongly connected. I cannot apply the formula we had earlier. Well, I know it's not strongly connected, but you could make it strongly connected, okay? Because this is like an exit node. If you create, are you ready? If you create an artificial link from S1 to S6, okay? So what I'm saying is that I don't have the graph with me, but if we do it like this, okay? the original graph looks like this, right? So I could create a dummy node. Is that okay? Not dummy node, a dummy link or dummy edge, right? So by creating a dummy link there, so this graph is going to be strongly connected. Okay, with that said, then we are ready to use the formula, right? So in this case, the whole thing is strongly connected. So let's count the edges. So we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 edges, right? There are 10 edges. So we have 10 edges. How many nodes do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 nodes, right? And we have only one strong component here. So the whole thing is one strong component. So here you can see the 3. So our cyclomatic number is 3 in this particular case, right? You say, oh, how about the second approach? The second approach is to count the bounded area. So we could count the bounded area. So apparently this is 1, okay? And this is 2, right? So that's the second bounded area. The third bounded area is here, so 3. So here you can see that by counting the bounded area, the cyclomatic number is also 3. Yeah, it should be 3, right? All right. How about the method I told you about? That is the number of conditions plus 1. By looking at this, you say, which node is a condition node? Can you tell which node is condition node? The condition node is going to be, is this one a condition node? No. Is this one a condition node? You say, yes, that's a condition node, right? This one? No, no, no. Is this one condition node? Yes, that's a condition node, okay? The others are not. So how many conditions do we have in this case? So it is number of condition plus 1. So how many conditions do we have? The number of conditions we have here is 2 plus 1. Okay, so here you can see that the cyclomatic number by counting the condition is also 3. Okay, so that's quite straightforward for this program. Cyclomatic number for this guy is 3. Okay. Okay, let's go to one that is a little bit more complex. Okay, the program actually is on the left, right? I'm sure you are familiar with this CSD notation. Okay, that's data cross notation, control structure diagram. Okay, so here you can see that. So the program graph is on the right. You say, how come this is a program graph? Okay. See here, we say that we want to refine. I might not have mentioned to you, but what we want in this class, is that for a decision is like this. For example, I have C1 and C2 and C3. So I have a decision is a compound decision. So it involves C1 and C2 and C3. Okay. So in that case, what we needed to do is that we needed to refine it into like this. C1, when it is true, I come here. When it is false, I check C2, okay? Oh, because this is ended together, right? So here I want to, so it is, that's not the right way, okay? So it is that when it is C2, if it is true, I check if C3 is true or not. When they are all true, I go to the next node, okay? So statement 1. If any of them is false, okay? False. If any of them is false, I'll go somewhere else, right? So in that case, what I'm saying is that I want every single node should have only one condition, okay? So each has only one condition. That's what we want in this particular class, okay? So each node should have only one condition. So you cannot say, oh, I put all the conditions together for a node. No, we cannot do that. We needed to refine it like this, okay? And that's what we needed to do in this class. So that's the same. That will be the same for your assignment and for your test as well. So it's awfully important for you to remember that. We needed to refine it into individual conditions. You say, why? Why do we care? Well, remember, when we calculate cyclomatic number, when we count our cyclomatic number, we count it by the number of conditions, okay? So in this case, if you put it all together, dump it all together, how can you count it, okay? It will be only one statement. So we really needed to refine it into individual statement, individual nodes, okay? With that said, so let's go back here. So here we have a program, okay? The program actually, well, those are declaration. We skip it. Nobody said you have to skip it. You could have a node 3 and a node 4 on top of it too, if you like. So here you can see that the first statement 5. So here you can see that this is a decision. Okay, this is a decision, and they are ended together. They're ended together. So here you can see that. So because they are ended together, I'm going to, for example, we may say, because there are 3 conditions here, I may call this one phi 1, this one phi 2, phi 3. That's exactly what we did, right? So here you can see that I may say, okay, phi 1, phi 2, phi 3. If all of these are true, if it is true, you check phi 2. True, you check phi 3, okay? If they are all true, you go to statement number 6. So that's number 6. If any of them is false, so all these links, they are all false link. So you go to number 9, okay? So you go to number 9. So here you do the same thing for 11. Statement 11, this is the simple condition, okay? So 11 just true or false. When it is true, you go to 12. So this is the true branch. This is a false branch, right? True branch, false branch. When you go to the true branch here, 12, go to the truth branch here. There are 2 conditions, so you have to refine it, okay? So here you can see that if it is true, and this is true also, you go to 13. You go to 13, okay? If any of them is false, you go to 15, okay? You go to 15. And the 15, again, there are 3 conditions, okay? So again, they are ended together. So true, you go to 16, okay? So, you needed to go home and then read this or study this carefully. Why the program graph is like this, okay? So with that said, the program graph is like this. Every single node, if it is a true or false node, you want to make sure that it has only 2 outcomes, okay? It has only one condition. Everyone should have one condition and the 2 outcomes, okay? All right. So my next question. You forgot my question? Okay, so my question is pretty straightforward. Ladies and gentlemen, what is the cyclomatic number for this graph? Okay, so my question is that what is the cyclomatic number for this graph? First you say, oh, it's tough. This one is not exactly. It is not strongly connected. So remember, how do we make it strongly connected? Okay, we can make it strongly connected by, for example, creating a dummy link, right? So here I say, okay, I can create this dummy link, right? So, so what is the cyclomatic number? Do we really have to count this? Okay, so here we say, I don't really want to count that. Okay, you can count it yourself. But you know, we may count the enclosed area. So here you can see, by counting the enclosed area, we may say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So if you count the enclosed area, it is 10. Okay, you can also count the number of edges, number of nodes. Okay, and then you can do that at home. Okay, by yourself. We will not do it here because you know it's no fun to count those. Okay, with the entire class. So here, the other thing is the number of condition plus 1. This one is easier to do. Okay, so ladies and gentlemen, are you ready? So shall we count the number of conditions we have here? The number of conditions. Is this one a condition? Yes, that's a condition. Is this one a condition? Yes. This one? Yes. Is this one? No, it's not. There's only one outcome. This one? No. This one? Yes. Okay, that's a condition. Okay. This one? Yes. Yes. This one? Yes. 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 This guy? Is this one a condition? No, it's not. Okay. This one? No, it's not. No, no, no. So are you ready to count the number of conditions we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So totally we have 9 conditions plus 1. Okay. Amazingly, it is also 9. Have you noticed that? So the cyclomatic number for this graph is also 10. Well, of course, it is 10. Okay. So here you can see that it is quite straightforward to calculate the cyclomatic number. So there are 3 ways you can do that. Okay. All right, let's go back to the slide. So this one, you know, now it becomes a piece of cake. Okay. All right, sometimes the graph, like the one we have just seen, so that's complex, too complex, I get dizzy, you know, with so many conditions. So, you know, you may condense to simplify the nodes, okay? So one possibility to simplify the graph is that you may condense the strong component, okay, like this one, okay? Have you noticed what is a strong component, by the way? Strong component is that, you know, if you go to one of the nodes, you could go to anybody, okay? So here you can see that this strong component N1, N4, N6, you know, maybe I can just condense it into one component, okay, like this, right? Like this one, okay? Because, you know, if I go to one, I can go to all of it. So that's one possible way to condense it, okay? The other way is that, of course, you can imagine that, you know, they all belong to the same distribution. Okay, maybe if I don't refine them, it will look like this. Okay, it should look like this, right? So it should look like this, and then yeah, you know, do you see that? See like this 12 and 1 and 2, you know, and 15, 1, 2, 3. I may put them all together, so I make it look nicer. Okay. Okay, you know, for other purposes, that's fine. Okay, for other purposes, this is okay. But let me tell you, in our class, okay, the one I don't want you to condense any of them, okay? So this is the graph. The one on the left, the refined graph, is what we want in our homework, in our test, in everything, okay? Why I want to do that? Because you are learning, you are students, and that's what I want, okay? Because you will not get confused, okay? So because this is the one we are going to use. Is that okay? I know that some of you don't like it, but that's just the way it is in this class, okay? Okay, now, actually, that's the same thing here. So I'm going to give you, give you some examples, okay? The two examples we have are like this, okay? This is a program 3. So you can see that this one actually is in the handout section. It's in the handout section, okay, of the on Canvas, okay? So, ladies and gentlemen, we are going to derive program graph for this particular program. How much time do you need to do this? Oh, I'm going to give you say maybe 5 minutes to do this one. Is that okay? Okay, so why don't you work on this yourself, okay? While I work on my program graph. My program graph is going to like this, right? So this is the program graph I have. I don't know how yours looks like, okay? So this program graph, as you can see, we start from statement number 35. So this program graph, sometimes you may say, oh, that's very confusion. You have the line number as the node name, but here I have the condition name as node number, and here I have the statement name. So this one, you know, this one just let you know that to show the program graph. Okay, the notation is not perfect, but the next one will be perfect. Okay, so here the program graph looks like this. So we have C1, right? Where's C1? C1 is right here. Okay, when C1 is true, you go to S2. When it is false, you go to C2. So here, this is the program graph. Okay, I'm going to give you maybe 30 seconds to make a copy of this. Okay, your 30 seconds is up, right? So here you can see that, okay, this is my program graph, okay? But you can see that it is not strongly connected. So how do you make it strongly connected? So here I have, I created an artificial exit, right? Although 47, if it is false, you come here. You come here. And then this is the dummy link that I created, right? So I'm not going to make this one a node, okay? So basically the dummy link is just from 47 to 35. Okay, of course you can always count the number of edges. You can always count that, but I'm not going to count the number of edges, okay? That would really mess up the drawing here. But, you know, what is the cyclomatic number here? So cyclomatic number, for example, if we have the strongly connected graph, again, the graph has to be strongly connected. So we count the number of bounded areas. So we have 1, this is 1 area, 2 area, 3, 4, 5. So we have 5 bounded area. So the cyclomatic number is 5, right? How about using the other method, that is number of conditions plus 1? The number of conditions plus 1, let's see. The number of conditions plus 1, okay? the number of conditions. Is this a condition? No. Is that a condition? Yes. Well, you already say that this is a C1, right? Is this a condition? Yes. This one a condition? No. This one a condition? No. This one? No. This one? Yes, because it has two outcomes, right? And this one? Yes. This one? No. No. So how many conditions do we have? The number of conditions we have is 1, 2, 3, 4. So we have the number of conditions we have is 4 plus 1, and then we reach the same conclusion. Okay, so cyclomatic number for this is also 5. Okay. Okay, and then finally we have another example. Okay, I think you really needed to go through the example, so you'll be able to do the homework. Okay, so suppose this is our program. So this is more realistic program. Actually, this is a real program. Okay, we just get one of it. Okay, part of it. So here you say, okay, this can we derive the program graph for this? So here, this one actually, I'm going to write the program graph for you. Okay, as we go. So this one, you say 34, statement 34. Statement 35, you know, they are just sequential. Okay, so you know, we can just say 33, it's a 34, and then 35, and then when we go to 36, right? 36 is a while loop. So here we say, okay, 36, that's a condition. If it is true, when it's true, you go to 37, 38. So we go to 38 when it is true. Okay. When we go to 37, when it is a false, where do we go? So if 36 is false, we actually go out. We actually go out. So we actually go to 47. 47 is a return statement. Okay, return statement. So for 39. 38, when it is true, we go to 39, okay? And then when it is false, we go to 41, okay? And then, so 41, when it is true, we go to 42. And then when it is false, we go to 44, okay? So here, and then you can see that we loop back here, we loop back here, okay? And then after we finish 47 or 44, 44 is also return statement. Have you noticed that? So in that case, we may create an artificial exit, okay? Artificial exit. So artificial exit is, but then this is not strongly connected. No, it's not strongly connected. You can make this one. You can move your exit to the entry node. Okay, if you move this link and that link, you move them all to 34. Okay, that will be fine. Okay, in that case, it will be strongly connected. You can do the others yourself, but let's do the way I like the most. That is number of conditions plus 1 for the cyclomatic number VG. The cyclomatic number is number of conditions plus 1. So how many conditions do we have? Ladies and gentlemen, you ready? This one? No, no. 1, 2, 3. So we have 3 conditions, right? So we have 3 conditions. So 3 plus 1. What is that? Do you remember, ladies and gentlemen? Oh, it's a 4, right? So you can see that we actually, it is actually 4, okay? it is actually 4. Okay, so if you want to count the number of areas, so you say 1, 2, 3. You may say, oh, you know, if you move this link, you count that. That's also 4 as well. Okay, so the cyclomatic number for this guy is 4 as well. So with that said, I think you have enough knowledge to almost enough knowledge to do assignment number 1. We need a little bit from next PowerPoint slide to do assignment number 1. Okay, so with that said, we are going to finish here. And I will see you in the next PowerPoint slide. Okay, see you next time. War Eagle.